discuss in the last class the concept of what is meant by limit superior and limit inferior of a sequence, of a bounded sequence, right. Let us just recall that once again. Suppose xn is a bounded sequence, bounded, of course all sequences are sequences of real numbers, so I need not say that separately, but okay, if you want you can make sequence of real numbers. Okay. Then we define what is meant by limit superior of xn, limit superior of xn, this is the notation lim sup. Okay. And what was the definition of that? We had taken that as first of all supremum over n bigger than or equal to k of xk, and then infimum over k, okay, infimum over k, right. Okay. All right, let us denote this by x superscript star, okay, x superscript star, okay. And then we also define what is meant by limit inferior of xn as n tends to infinity. This is a standard notation lim inf, okay, and there the roles are interchanged, okay, that is this is supremum over k, infimum over n bigger than or equal to k, sorry this should have been xn, okay, xn, okay. And let us denote this by x, let us say subscript star, okay. This is Rudin's notation, okay. What we have seen is that the sequence may or may not be convergent, that is limit may or may not exist, but once the sequence is bounded these two numbers will always exist, okay. Limit superior and limit inferior will always exist for every bounded sequence, okay. Now let us see a few properties of these two numbers, okay. First of all what we have seen is the following, that is if this number supremum over xn n bigger than, okay, we had denoted, remember we had denoted this number as alpha k, right, okay, and similarly infimum of xn for n bigger than or equal to k, this number we had denoted as beta k, okay, alright. And what we had seen is that alpha k is a monotonically decreasing sequence that converges to x star which is its infimum, and beta k is a monotonically increasing sequence and that converges to this number, okay. And of course since these are supremum and infimum over the same set, we should always have beta k is less than or equal to alpha k, right, beta. So what we can say is that beta k is less than or equal to alpha k for all k, okay. But we can say something more, okay, that is suppose I fixed a particular beta k, okay, right, then beta k is less than or equal to alpha k, alright, and so okay, or in other words since beta k is less than or equal to alpha k for all k, okay, what we also must have is that this x subscript star is a limit of beta k, okay, and x superscript star is limit of alpha k, okay. So is it clear that that should imply that limit inferior is always less than or equal to limit superior, right, that is true, okay. In fact we can say something more, since x star is supremum over beta k, all of these x star will be bigger than or equal to beta k, okay, and similarly all of this alpha k will be bigger than or equal to x star, okay. So what we can say is this, that is for all k, that is beta k is less than or equal to this x subscript star, this is less than or equal to x superscript star, and this is less than or equal to alpha k for all k. Okay. And because of the way in which we have defined these numbers alpha k, for all n bigger than or equal to k, all xn's will lie between these two numbers, okay. Let us also recall that, okay, that is we can say that beta k is less than or equal to xn, this is less than or equal to alpha k for all n bigger than or equal to k, okay. Okay. Now let us see something more. Okay. Suppose we are given some epsilon bigger than 0, okay, let epsilon, okay. Then we can say that since alpha since this x superscript star is an infimum over all these alpha k, okay. Again, infimum is greatest lower bound. So if I take any number bigger than that, okay, that is not going to be a lower bound, okay, that is not going to be a lower bound. So what does it mean? That there will exist some number, which is bigger than that. In other words, for every epsilon there will exist some alpha k which is bigger than x star, sorry, which is smaller than x star plus epsilon, right. So then you can say there exists, for example, suppose I call k naught, there exists, let us say k naught in n such that alpha k is less than x star plus epsilon. Alpha k is strictly less than x star plus epsilon, okay. Right. Okay. Now if so, let me call it alpha k naught, okay. Alpha k naught is less than x star plus epsilon, okay. But alpha k is a decreasing sequence, okay. So if this happens for one k naught, all for k bigger than or equal to k naught, all alpha k are less than or equal to this alpha k naught, okay. So they will be less than x star plus epsilon, okay. They will be all less than x star plus epsilon, okay. So we can say, so then we can say that then for all k bigger than or equal to k naught, alpha k is less than x star plus epsilon. Right. Okay. But again remember this, okay, for n bigger than or equal to any k, xn is less than or equal to alpha k, okay, and alpha k is less than x star plus epsilon, okay. So using this we can say that for all n bigger than or equal to k naught, in fact this is what I wanted to have, for all n bigger than or equal to k naught, xn is less than x star plus epsilon, okay. Okay. All right. So what did we prove? That for given any epsilon there will exist some k naught, such that for all n bigger than or equal to k naught, xn is less than x star plus epsilon. That is clear? Okay. All right. What can we say similarly for this number? They will say, for example, that k naught may be different, okay. There will be, we can say there exists some k1, for example, such that, okay, we can say that similarly, there exists k1 in n such that, okay, I will skip this step, such that for all n bigger than or equal to k1, x star minus epsilon less than xn, okay. All right. Okay. Now this is a small observation, but we have proved something very important here, okay. See, given any sequence, this x subscript star is less than or equal to x star always, okay. But suppose those two numbers coincide, okay, let us say for some sequence those two numbers coincide, okay, then what does that mean? That means that means for epsilon I can take let us say n naught, which is maximum of k naught and k1, and for that n naught, for that n bigger than or equal to that n0, okay, all xn will lie between x, I think this should have been x, okay, right. Suppose x star equal to x suppose limit superior is equal to limit inferior, and suppose we call the common value x, okay, then this argument shows that we can always find a number n0 such that whenever n is bigger than or equal to n0, okay, xn lies between x minus epsilon to x plus epsilon, right, okay. In other words, the sequence converges, right, okay. So what did we show? That if, let me write this as a theorem, okay. If x star is equal to this, then xn converges to this common value. In fact, we can say that xn converges to this common value. Okay, I already told you what is the proof. Okay. Already. Now, what about the converse? Suppose xn is a convergent sequence, okay, then can we say that these two must coincide? Okay, okay. Let us say, let me just write that, okay, we'll, okay. Conversely, if limit xn as n tends to infinity is equal to x, then x is equal to this limit superior, this is equal to limit inferior, okay. Okay. Now this part we already proved, okay. This part we, let us just prove this other part, okay. Suppose this happens, okay, suppose limit of xn as n tends to infinity is equal to x, okay. All right. Let us take some epsilon bigger than 0, then we know that for this epsilon, since this happens, there exists n0 in n such that for all n bigger than or equal to n0, we must have mod xn minus x less than epsilon, okay, mod n xn minus x less than, I shall write it in this form, x minus epsilon less than xn less than x plus epsilon, okay. In other words, for all n bigger than or equal to n0, okay, x minus epsilon less than xn less than x plus epsilon, okay, all right. Now suppose I take some k bigger than or equal to n0, okay. Remember, all the xn's are lying, so let us say this is x, all the xn's are lying between this x minus epsilon and x plus epsilon, all n xn bigger for n bigger than or equal to n0, okay. Now suppose I take k bigger than or equal to n0, okay, then what can I say about alpha k and beta k? See, for n bigger than, let us take this inequality, for all n bigger than or equal to n0, I know that xn bigger than x plus epsilon, okay, okay. Let us say k is equal to n0, okay. Suppose k is equal to n0, okay, and so for all n bigger than or equal to that k, xn is less than x plus epsilon. What is alpha k? Alpha k is supremum over of xn for n bigger than or equal to k. So what can you say about that? If each of this xn is less than x plus epsilon, that alpha k should also be less than x plus epsilon, right? Alpha k, so this implies that, and not only for n0, but this will be true for every k bigger than or equal to n0, right, okay. So alpha k is less than x plus epsilon, okay, alpha k is less than x plus epsilon for all k, or maybe less than or equal to, okay. Okay. Similarly, xn is bigger than or equal to x minus epsilon, all xn's are bigger than x minus epsilon, okay, and beta k, what is beta k? beta k is infimum over all those xn, each of this is bigger than x minus epsilon, okay. So the infimum should also be bigger than x minus epsilon. So what we get here, that is x minus epsilon is less than beta k, okay. Alright, now look at this inequality, okay. I will insert that x subscript star and x superscript star between those beta k's and alpha k's, okay, right. So what I can say is that x minus epsilon, so let me just take that, so this implies, okay, so I can say this is less than or equal to x subscript star, this is less than or equal to x superscript star, and that is less than or equal to alpha k, okay. I shall rewrite this once again, okay, here. I'll continue here. Okay, so what we have proved is this: for all n bigger than or equal to n0, x minus epsilon less than b, okay, less than or equal to beta k, less than or equal to x subscript star, less than or equal to x superscript star, this is less than or equal to alpha k, and this is less than or equal to x plus epsilon, okay, right, okay. So does it follow from here that if I look at the difference between x star, these two numbers, limit superior and limit inferior, okay, then that difference is less than or equal to 2 epsilon, right, okay, because the whole thing is like that means these two numbers, limit superior and limit inferior, both of those numbers lie in this interval x minus epsilon to x minus epsilon, okay. So the difference between them must be less than 2 epsilon, okay, right. So what we can say, and we already know that this is limit superior is bigger than or equal to limit inferior, okay. So combining all this, we will get this inequality 0 less than or equal to limit superior minus limit inferior, and this is less than or equal to 2 epsilon. This should be okay. And now the argument is usual, epsilon was arbitrary, okay, right. What inequality written here is true for every epsilon, okay. So the only way in which this can happen is that these must be same, okay, this must be the same, okay. So whenever a sequence converges, its limit superior and limit inferior equals the limit of the sequence, okay. And conversely, if the limit superior is equal to limit inferior, okay, then the sequence must converge, and it must converge to that common value, okay. So this is a good way of deciding whether a bounded, of course if a sequence is not bounded, it is not convergent, okay. We already shown that every convergent sequence is bounded, okay. So there is no question there, okay. If a sequence is bounded, you can always calculate its limit superior and limit inferior, and then decide whether it is convergent or not, okay. So this field should always work in most of the sequences, okay. Now let us also say something about the subsequences, okay, right. Let us say that xn, let us say that xnk is a subsequence of x, okay, right. Then you can say that if this, I think this is a bad notation, let me use x and j because k we have used earlier for something else, okay. Let us say x and j is a subsequence of xn, okay, right. Then what we observed here is that for n bigger than or equal to k, xn lies between beta k and alpha k, okay, xn lies between beta k and alpha k. So what follows from here is that if this nj, if this index nj is bigger than or equal to that k, then that xnj should also lie between beta k and alpha k, okay. Xnj should also lie between beta k and alpha k, okay. So in particular, if this xnj is a convergent sequence, if xnj is a convergent sequence, then that also should lie between beta k and alpha k for all k, okay, for all k, and in a similar way again we can prove that that limit must lie between these two numbers. Okay. So if a sequence has a convergent subsequence, then the limit of that convergent subsequence must lie between limit inferior and limit superior. Okay. So let us say that if xnj is, let us say if limit of xnj as nj tends to infinity is equal to, let us say, L, okay, then L lies between these two numbers, limit inferior less than or equal to L less than or equal to limit superior. Okay. Okay. We can also observe one more thing, okay, and that is the following. Okay. That means if you take any subsequence of a sequence and that subsequence is convergent, then its limit must lie between limit inferior of the sequence and limit superior of the sequence. Okay. So if you take this interval, let us say if you take this interval x x subscript star to x superscript star, limits of all convergent subsequences must lie in that. Of course if the sequence is convergent, those two are going to coincide, and then obviously we have already shown that if a subsequence will also converge to the same limit. Okay. But if the sequence is not convergent, then subsequences may converge to different limits. Okay. But all of them must lie between these two numbers. Okay. All of them must lie between these two numbers. Further we can show that you can always find a subsequence which converges to this number as well as to this number. Okay. Right, and that is something you can see again from here. Okay. You can follow in a similar way. For example, suppose see here we have seen that given any, let us just recall this again. What we did here, given any epsilon bigger than 0, we have shown that there exists k naught in it such that alpha k naught is less than x star plus epsilon. Okay. Right. Now use the fact, and then so for all k bigger than or equal to k naught, alpha k is less than x star plus epsilon. Okay. Right. Now alpha k is a supremum. Okay. Alpha k is a supremum for xn. Let us recall it. Okay. What was alpha k? Alpha k is a supremum of xn for n bigger than or equal to k. Okay. Okay. Now here I have used only what happens if you take x star plus epsilon, but suppose you take alpha k minus epsilon. Okay. If you take alpha k minus epsilon, then you can always, it will be in that there exists always some xn bigger than or equal to k such that xn is bigger than alpha k minus epsilon, right. Okay. So what it means is that okay, let me just write here. Okay. Given any alpha k, you can say that there exists, say suppose I call that nk bigger than or equal to k. Okay. There exists nk bigger than or equal to k such that alpha k minus epsilon is less than x nk. Of course this nk may depend on this epsilon also. Okay. This nk may depend on this epsilon also. Okay. And of course this is less than alpha k. X nk is less than or equal to alpha k because alpha k is the supremum for all n bigger than or equal to k. Okay. All right. So what it means is that for each k I can find some number from the sequence which is arbitrarily close to alpha k. Okay. Which is arbitrarily close to alpha k. Okay. So, and since this is true for every epsilon, I can make some choice of the epsilon. Okay. Okay. I can make some choice of the epsilon. Okay. For example, I could have started with taking epsilon as, for example, I could have started with taking epsilon as something like, let us say 1 by k. Okay. All right. Then that means for each k I can find some xn k such that alpha k minus 1 by k is less than xn k less than or equal to alpha k, right. Okay. Now we know that this alpha k converges to this x superstar. Okay. X superscript star. What about alpha k minus 1 by k? That will also converge to this x superscript star. Okay. So that means what should happen to this subsequence x and k? again use the sandwich theorem, okay. So that should also converge to this limit superior, okay. So what did we prove? That there exists a subsequence, which converges to the limit superior, okay, that is okay. Alright, so let us just write that here. Okay. If xn is a bounded sequence, then it has a subsequence converging to let us say limit superior of xn. So limit superior of xn as n tends to infinity. Okay. In a similar way, we can also say that it also has a subsequence converging to limit inferior of xn, okay, also. Okay. Then it has a subsequence converging to limit and a subsequence converging to limit inferior of xn. Is it clear whatever we have said so far? Okay. All right. And so if the limit superior and limit inferior are different, okay, then it means we can find two subsequences converging to two different limits, okay, and that will also mean that sequence is not convergent, okay, but which is something we have seen earlier also. But this has one very important consequence, okay, and what is that? It means that every bounded sequence has a convergent subsequence, okay, and this is a very well known this is known as the Bolzano-Weierstrass theorem, a very fairly well known theorem, okay, Bolzano-Weierstrass theorem. Okay. Of course it does not say like this, it says that every bounded sequence has a convergent subsequence. Has a convergent subsequence. One of the important theorem in elementary real analysis, okay. In fact you can see that we have proved here something more, okay. We have said that there exists a subsequence and we also said something about its limit, okay. Of course every convergent subsequence, its limit must lie between limit inferior and limit superior, okay, that is something we have seen already, okay. And important thing to realize here is again that all this thing follows basically from the LUB axiom, okay. The whole idea of defining a supremum, the proof that every monotonically increasing sequence which is bounded above has a limit, all those things are used in this development, okay. Okay. Now let us go to another important concept, what is known as Cauchy sequence. Okay. Again let us say that suppose xn is a given sequence and we will say that a sequence xn we shall say that this is a Cauchy sequence, the sequence xn is said to be Cauchy. If what it should happen is that if you are given any epsilon bigger than 0, if for every epsilon bigger than 0 again there should exist some n0 in n such that if you take any two numbers n and m bigger than or equal to n0, then the difference between corresponding xn and xm should be less than this epsilon, okay. That is then such that mod xn minus xm is less than epsilon for all n and m bigger than or equal to n0, okay. Okay. What does this mean? That given any epsilon, see there is no idea of limit involved here, okay. What it means is that given any epsilon, the terms of the sequence xn and xm come arbitrarily close to each other for large values of n, okay. For large values of n we can make xn and difference between xn and xm arbitrarily small by taking n and m big enough, okay. Roughly speaking, when we say that a sequence is convergent, it means that for large values of n all xn go close to that value x, okay. Whereas for Cauchy what it means is that for large values of n and m each of the elements xn come close to each other, okay. Now intuitively it is clear, if all of them go close to some one point x, they should also come close to each other, okay, right. That is what is expressed by saying that every convergent sequence is Cauchy, okay. Let us just quickly see the proof of that. Okay, so every convergent sequence is Cauchy. Okay. So suppose we take a convergent sequence xn and we should show that it is Cauchy, okay. So suppose xn is a convergent sequence suppose it converges to x, okay. So convergent sequence converging to x. Then we have to show that this happens, okay. We have to show that this happens, okay. So let us take epsilon bigger than 0, okay. You will see that the proof follows simply by the elementary properties of this absolute value function, okay. So we can say then there exists n0 in n such that for all n bigger than or equal to n0 what we have is mod of xn minus x is less than epsilon, right. But I can as well take epsilon by 2, okay. Whether it is epsilon or epsilon by 2 or epsilon by 3 it does not matter, okay. Okay, you can take any small number basically, for any small positive number you can find some n0, okay. So now take n and m both bigger than or equal to this n0, okay. Let n and m bigger than or equal to n0, then look at mod xn minus xm, okay. What is to be done is clear, okay. Just add and subtract x, okay. So this is less than or equal to mod xn minus x plus x minus xm, and since each of this is less than epsilon by 2, okay. Right. Okay. Now the obvious question after this is what about the converse, okay. Can we say that every Cauchy sequence is convergent, okay, right? And the answer is that it is true for real numbers, okay. That is a important property of real numbers, that every Cauchy sequence of real numbers is convergent, okay, and that is expressed by saying that real line is complete, okay. We shall discuss what is meant by completeness little later when we discuss metric spaces, okay. This property is not held by all kinds of numbers. For example, if you take a sequence of rational numbers, you can find that sequence of Cauchy sequence of rational numbers but not converging to rational numbers, okay. But that is but the real line has this property that every Cauchy sequence of real numbers is convergent. There are various ways of proving this. One can prove, for example, that if a Cauchy first of all we can prove that a Cauchy sequence is bounded, okay. That is very easy, okay. I will give that to you as an exercise, okay. Exercise, prove that every Cauchy sequence is bounded. Every Cauchy sequence is bounded. Okay. Then once we know that a sequence Cauchy sequence is bounded, it has a convergent subsequence, okay. And one can show that if a Cauchy sequence has a convergent subsequence, then the sequence itself converges, okay. Okay. So try to prove this on your own this way, okay, because it has a convergent subsequence means what? Suppose that sequence converges to, let us say, some number x, it means all those terms of that subsequence go close to x, okay. But it is a Cauchy sequence, okay. So in case of Cauchy sequence we know that all the terms go close to each other also, okay. So that means every term must go close to that number, okay. This is the idea of the proof, okay. You can use this idea and prove that use this method to prove that every Cauchy sequence converges, okay. But let us use something else that also I have already mentioned to you one article by Professor Kumaresan, okay, that role of LUB axiom, okay, that also contains a more direct proof of this, that is how to use LUB axiom directly to show that every Cauchy sequence is convergent, okay. So you can also have a look at that proof, but it is better to give the proof directly by using this idea of limit inferior and limit superior, and let us try to do it in that fashion, okay. The idea here is simple, okay. See this mod xn minus xm is less than epsilon for all n and m bigger than or equal to n0, okay. Okay. So suppose the sequence is, I will just give an idea and you can write the proof on your own, okay. See, suppose I take m is equal to n0, okay. Okay, suppose I take m is equal to n0, will it mean from will it follow from that it will mean that mod xn minus xn0 is less than epsilon, okay. That it will mean from that for all n bigger than or equal to n0 x n0 minus epsilon is less than xn less than x n0 plus epsilon. Okay, all right. Then what can you say about this beta case and alpha case from here? Suppose you take k bigger than or equal to that n0, then the difference between alpha k and beta k must be less than, can you say from here that for this will imply that is for all n bigger than or equal to n0 beta k minus alpha k must be less than 2 epsilon. Do you agree? Okay. Remember all of xn are lying between xn0 minus x, okay. So beta k for k bigger than or equal to n0 beta k must be less than xn0 plus epsilon, okay. Sorry, alpha k must be less than xn0 plus epsilon and beta k must be bigger than xn0 minus epsilon. So difference between beta k minus alpha k must be less than 2 epsilon. Okay. Will it follow from here that the difference between limit superior, this is true for all k bigger than or equal to n0, okay, for all k bigger than or equal to n0, okay. So will it follow from here that see this beta I should have written it other way because alpha k is going to be bigger, okay, alpha k minus beta k, right, okay. So alpha k minus beta k less than or equal to epsilon for all k bigger than or equal to n0, and what does this mean? This means limit superior minus limit inferior less than or equal to 2 epsilon, okay. And again now the usual argument, since epsilon was arbitrary, okay, since epsilon was arbitrary, this means that sorry, again this should have been okay. Since epsilon was arbitrary, this shows that limit superior and limit inferior coincide, and we have already shown that when that happens the sequence must be convergent, right? Okay. So what did we prove? That every Cauchy sequence of real numbers is convergent. Real numbers is convergent. Okay. So as far as the sequences of real numbers is concerned, okay, there is no difference between a convergent sequence and a Cauchy sequence. Every convergent sequence is Cauchy and every Cauchy sequence is convergent. Okay. This is quite useful in several other concepts which we shall see subsequently. Okay. So now if we want to give an example of a Cauchy sequence, in case of real numbers it has to be an example of a convergent sequence, okay. And if you want to give an example of a sequence which is not Cauchy, it has to be an example of a sequence which is not convergent, okay. So since these two concepts coincide for the sequences of real numbers, there is no point in discussing separately the examples of sequences which are Cauchy or not Cauchy, etc. Okay. So we shall not do anything like that. So let us now proceed further with the concepts which is again closely related to the concept of the sequence, okay, and that is what is called series, or sometimes also called infinite series. Okay. What is an infinite series? One can say that infinite series is basically a sequence, okay. It is a sequence. So suppose xn is a sequence in R, let us say sequence is a sequence in R, okay. Then we just look at this expression sigma xn, n going from 1 to infinity, okay. For the time being we shall say that this symbol may or may not have any meaning, okay. This may or may not mean anything, okay. At a certain see, if we take only finitely many terms, it means the addition of those real numbers, okay. But in general addition of infinitely many real numbers has no meaning in general, okay. But under certain conditions we can give a meaning, and that is what the theory of infinite series deals with, okay. So let us say, suppose we take the first n terms of this sequence, okay, and denote it by some new number. Suppose I call Sn as x1 plus x2 etc. up to xn, that is take first n terms, okay. Since we are going to use this fairly often, let us use this notation sigma xj, j going from 1 to n, okay, sigma xj, j going from 1 to n. This Sn is called a partial sum of this series, okay. We say that Sn is a partial sum of this series, it is called partial sum. I will give some notation for this series. Suppose I call this series 1, okay. This is called partial sum of the series 1, okay. So this is a new sequence, okay. That means what you do is, given a sequence xn, you form a new sequence which you call sequence of partial sums, okay, and after this whatever you want to define about the series is defined in terms of this new sequence, okay. So this Sn, this is a sequence of partial sums, okay. Remember that xn and Sn determine each other, okay. Once you know the sequence xn, you can find a sequence Sn by this method. Converse is also true. If you know the sequence of partial sums, you can easily find the sequence xn. How is that done? S1 is anyway x1, okay, but if you know S1 and S2, you can find x2, right? If you know S2 and S3, you can find x3, right? Okay, so in general what we can say is that so Sn plus 1 will be x1 plus x2 etc. up to xn plus 1. So we can say that xn plus 1 is Sn plus 1 minus Sn, okay, and x1 is S1. So if you know Sn, you know xn, and if you know xn, you know Sn, okay. So both are determined by each other, okay. So we just look at this sequence Sn, okay, and if this sequence converges, okay, we say that the series converges, okay, we say that the series converges, and whatever is the limit of this sequence, we call that the sum of the series, okay. So if Sn converges to S, if Sn converges to S, then we say that the series sigma xn n going from 1 to infinity converges to S. Okay, and this S is called the sum of the series. Okay, denoted by this, okay, denoted by sigma n going from 1 to infinity xn is equal to S. Okay. So only in this special case this expression sigma xn n going from 1 to infinity has a meaning, okay. Only when the series converges, okay, we can talk about its sum. Okay. Sometimes what we have called convergent series is also called, some books also like to call it summable series, okay. Convergent in case of series, summable is same as convergent, okay. You can see the reason why, okay, because it means that the series can be summed, okay, you can find the sum of the series, that is the meaning of summable, okay. Alright, you can make a few observations here, since everything that we are going to talk about series is going to be in terms of the sequence of partial sums, okay. It does not matter, for example, whether you start from 1 or 0 or 2 or any such thing, okay, right, okay. So one more thing, just as we have defined the what is meant by convergent, okay, in a similar way you can, if this is not the case, if the sequence Sn diverges, we say that the series diverges, okay. If the sequence Sn, if the sequence of partial sum is not convergent, it means it is a divergent sequence, we will say that the series is divergent, and in which case this has no meaning, okay? There is no such thing as the sum of the series is equal to S, okay, alright. Now we know that given any sequence, if you let us say remove a finite number of terms from that sequence, the remaining sequence is also going to be convergent, okay, right. If you add a finite number of terms to that sequence, either be at the beginning or somewhere in the middle, that new sequence is also going to be convergent, okay. So what follows from that about the series, whether a series is convergent or divergent will not matter if you add a few terms to the series or if you remove few terms from the series, okay. The whole behavior depends on what happens for the large values of xn, okay. The convergence or divergence of the series depends on how xn behave for large values of n, that means again in our terminology for n bigger than or equal to n0, okay. You should be able to say something about xn for n bigger than or equal to n0, that is going to determine the convergence or divergence of a series, and that is why it does not matter whether I start from n equal to 0 to infinity or n equal to 1 to infinity or 2 to infinity or minus 3 to infinity, starting point does not matter, okay. It does not matter in the sense, it does not matter to decide whether a series converges or diverges. It does not matter does not mean that the sum will not change, sum will change, okay. That is, if you start starting from x1 plus x2, you start from x0 plus x1 etc., that x naught gets added to each of this Sn, so sum will become that original sum plus x naught, okay, that will change, that is okay, okay. The sum will change, sum will depend on where you start, okay, but whether the series converges or diverges, that will not depend on what is the starting point or whether you take away a few terms. So either adding or removing a finite number of terms to a series does not alter its behavior as far as the convergence is concerned, okay. Alright, so with that we will stop for today. We shall see methods of deciding how the series converges or diverges in next.